something else, right? NAVD-ADA with the 2001 adjustment. So, so even with the datum difference, you can see probably, depending on where you are, 6 inch difference. So if you didn't check verify your vertical datum, then you're like, hey, our survey shows it's lower. So they modify your channel and everything, but at the end you realize that you should, if they were on the same vertical datum, probably very consistent. So that's very important. So vertical datum will always have to verify. Okay, and then the second one, this is always it's a must, it's a required. So before you start a project, you gotta know, what criteria you should be following, and then also the version of the criteria, the manual. This may be the later one, the more recent ones. They make some updates, so you also have to be aware of that. Okay, and then we go to the hydrology, and then of course at the beginning when you are selecting your methodology, that's the first part before you carry out your work. So you need to know what's your drainage area size. If it's under 200, then very likely it will be rational method, or sometimes this is Saronov curves. This is what we use in Harris County flood curve. And then I know that some other counties they also have a similar method. It's a quick peak flow rate estimation formula based on your area and then your impervious cover. Then you can estimate what peak flow you would get. Some counties they have their own. So in Harris County, there's this one called Saronov curve. If Wilco has one, then you can use it too. Not so sure. I couldn't find it. So
and even just to throw in there, for maybe like before you start using the checklist, tailor it towards Williams County, because even like the ranges here up to 640 acres, that's more of a Harris County.
Yeah, it's like HCFCD. Is that Harris County
Flood Control District? Yeah, yeah. So you might want to verify. Modify the spreadsheet a little bit, but in general, the concept should follow. So depending on so usually the break point is 200. So under 200, you apply a rational method. That's pretty standard. And then for the NRCS method, as we mentioned, it goes for from 0 to 2,000. Okay, since there's 200 acres that overlap, so typically you would stay with rational method for anything on 200, and from 200 to 2,000, you could use the NRCS method or the TR55. So that's that. So that's the standard.
For the SES.
All the okay. Yeah, so that's the standard approach. And then also what we have here, these can be changed. It doesn't have to be 600. Then you can use HMS. So HMS can be used for everything. And this also what we include here. This is a regression method. That's if you're working textile project. Then for regression method is very suitable for anything that's bigger than It's a 10 square miles. Yes, yeah, that's according to TechStop. So they had that regression method. So anything that's greater than the 10 square miles, then the regression method will be very, very suitable.
And it can't be too urban, I think.
It can be too
Can't
urban.
be too urban.
Yeah, it's usually a very rural area. Okay. Let me see. Okay, so this one we haven't covered this time because the clock unit hydrograph, this method for TCNR, this is a this method is used for say your drainage study or your hydraulic study requires any unsteady state simulation, meaning that a swim typically will be swim or unsteady head grass. But I would say mostly it's for swim, for roadway drainage that you have a storm sewer system, or you have any underground, sewer system, and then you have a surface system too. Then if you use a swim for roadway project, especially your drainage areas are usually very small, so less than 200. But as we mentioned that if you use rational method, you will only get a peak flow rate. But for an unsteady state simulation, you need a hydrograph. So this method here, this is kind of the way I see it. This is just a workaround, so that the concept behind this method is, since every drainage area we will have a type of concentration, right? So then we would in HMS we would have an initial R value, then we just keep iterating R value until the peak flow rate of your hydrograph matches the peak flow derived from rational method. So that's just, I mean, the way I see it's not really like a physically based, because TC you derive from your drainage area, but once you start iterating your R is the storage factor. So when you start changing your R factor to make it match your rational method peak flow rate, the physical meaning is already gone. So it's just like a parameter fitting exercise to make it match. And that's it. There's not really any derivation or any meaning behind it. You just wanted to create a hydrograph that has the same peak flow rate, and then you can enter it in your swim model so it can run. So that's it.
Yeah, and there's like a 1-page slide in the PowerPoint, but we didn't think I don't think you guys use that, so I'd say we didn't run through it.
Yeah. But later on, once you get to that stage, if you need it, then we can certainly go over it. Then after that, then that's for the area. So you check your area, you check your methodology, make sure you're using the right equations. And then after that, and then you start checking. This is I will call this like data pre-processing phase. Okay. So this is all, like you can tell, this is all GIS based, right? So whether you have any imagery, if you check your imagery, does it looks like it's in the right area, or maybe the client or the data you collected, you put it over your imagery, and then you realize it doesn't look like my project, right? So things like that. Yeah. And then also check processing, also confirm the LiDAR source. So it could be, we're lucky that in Texas there's a TextGeo that's the only data set that you get. But sometimes, let's say for example, for subdivision, because the area is much smaller, right? So they can even use drone fly, like a drone imaging or drone LiDAR that will give you very, very, very fine resolution. But that's for maybe for your neighborhood or for the subdivision. So drone flown LiDAR will give you like a very, very good uh, uh, information or precision, total information. But the drawback for that is also only for small area. So so just make sure that your data source is good. Uh, Let me see. And then the next one, when you are doing your, so you have your terrain, then you start doing your, okay, so this is about your watershed delineation, right? So you want to make sure that, so we carried out the watershed delineation through, the GIS practice, GIS exercise. So you use everything is automatic, right? So this is what we discussing when we're doing the HMS exercise. So we have a terrain. So the last one is you want to make sure your terrain coverage is big enough. So so you're not missing a part of your your drainage area. And then also we want to make sure that when you are doing your drainage area delineation, you want to make sure your boundary makes sense. It's not cutting through a building, or if there's a roadway, you need to make a proper adjustment. Okay, so that's that. Then after drainage area, then you go into your longest flow path, and then also you will check your slope and things like that. So I think we also went over this. So the flow path that you select, there could be multiple paths, right? So we want to select the one that makes sense. The way the way I would do it would be the most efficient way for the flow to get to the outfall. So that's that. And then, so when you're doing time of concentration, the derivation, so you want to make sure, because you will have to draw the path and then you have to extract the underlying terrain along that path. So you want to make sure when you are determining the slope of that section, that profile that you cut, you want to make sure you pick make the right uh, calculation for slope. Sometimes you will see that it could be multiple breaks along that your longest flow path. Then in that case, you might want to maybe split your longest flow path to several sections. If the slope is really changing so much, then you can't just assume like an average slope from the beginning to the end. That's not really that representative of that flow path. So things like that, you have to be very careful. What else? Slope and elevation outliers. Yes. So when you extract the elevation profile along your longest flow path, since everything's digital, right? So and then you're extracting the terrain information from your LiDAR. So where you're drawing the line, the path that you're taking, sometimes it could be, maybe you touch the building or touch some structure that's a little bit higher than the entire path. So when you look at your profile, you can probably see there's a big jump. So things like that, outliers you should also remove. So that way you get a representative slope along your flow path. Okay.
And hopefully if you can start using the surface, you can start visualizing that surface, because I don't know how you're getting your TC slopes for now.
Yeah.
It's like, looking at the start contour and contour distance, yeah.
Mhm.
And then for the last one, so this one probably, I was thinking in this area, the slope should probably be higher because it's very hilly here. So just make sure that the slope that you derived, is reasonable. Okay. And then after that, so we've got from watershed delineation, we got the second one is the flow path, time of concentration. And then, yeah, so Teresa also mentioned about this part. So when you're doing, preparing all your polygon for the shape files, make sure when you are, when you're creating your polygons, they are matching perfectly. So that meaning that there's no gap between, let's say, polygon, and then you have a gap in between, or you have little overlapping. So if there are elements like that, so then when you really calculating, let's say, your drainage area, then you'll realize that the total drainage area is not going to be the summation of your sub drainage area, because all these gaps or overlaps, so realize that there's some discrepancies there. So make sure you're doing your work. It's not very rough. It has to be, well prepared.
Yeah.
And that's important because if you do it right the first time, or you are always very careful how you produce your work, then at the end you don't need to come back and fix a lot of stuff. Okay. So that's the shapes and everything. What else? Oh yes, of course, projection is very important. Um, text dot or even working with design and the analysis. We've already seen that surface versus grid, right? So there's some projection transformation that's required to make sure everything's lined up properly. So that's that. And okay, so whatever.
And some of those things apply, like if you're doing the hydrology in GIS, like where it talks about the shapes and links in your attribute table. Because in GIS, when you make these shapes, it'll have a column for like its area, its length, its slope, which is typically how we work. Like we have an Excel, we make the data in GIS, and each shape file has an attribute table. And that's where we put like our slopes, our channel characteristics, and then we just copy and paste that into our Excel that calculates our flows, our peak flows.
All right. That's good. Okay. And then the next part, so we have longest flow path. Then the next one will be calculating time of concentration. So there are several methods to calculate the time of concentration. So the first part, that's these categories, so-called velocity based. It's very common, and then very simple to use. So that the idea behind that is you have a velocity, and then you have your length of your channel, and then you just use that velocity and then the length that you'll be able to calculate the corresponding time of concentration.
Right.
But in that case, the velocity is already predefined. So what you usually see is that, okay, stone sewer, 3 feet per second or 5 feet per second. If it's a ditch, then it's 1.5 or 2, something like that.
Where do you find that in the?
It's usually it will be specified in your drainage manual.
Oh, okay.
So that's just like you will find a table that will specify
Like text dot hydrology or
even text dot or even county too.
Okay.
Usually county will have its own. So you will see different conduit type, stone sewer versus ditch versus channel, like that, and they all have different assigned velocity. And then you can use that to determine your time. So that's one category. And sometimes people feel like that's too not sophisticated enough. So then you will use this is a different method. So there's this NRCS method. So the entire flow path is divided into three different sections. So you have your so the first one's overland flow, right?
Like this is the one I usually use.
Yeah.
The sheet flow, shallow concentrated,
yeah.
and channel.
Yeah, sheet flow, shallow concentrated, and then the last one is the channel flow. Thinking this area also Kirby pitch. I don't know if it's
Oh, yeah.
applied up here.
Think
Yeah.
so.
So if you look at the Kirby pitch method versus the NRCS, so NRCS you have three terms: the sheet flow, shallow concentrated, and channel. But the Kirby pitch is only two: sheet flow and the shallow concentrated. So the way I see it is the shallow concentrated, that part essentially, if you look at the equation and then the concept between the two methods, it's just the lump together, shallow concentrated and the channel part from the NRCS method is coming together.
Okay.
So you can, so this is also decided by your drainage criteria. Okay. So after that, then you make sure, so we got drainage area delineation, longest flow path, and then you determine your time of concentration. Then the next one is to make sure that we're going to calculate your peak flow. So you want to make sure your runoff coefficient is properly assigned based on your land use category. You want to make sure that this also it should be clearly defined in your drainage criteria manual. Different area they will have a little bit different C values. Okay, so make sure you apply the proper runoff coefficient when you're doing your peak flow calculation. Okay, and then sometimes there are like like special requirement. For example, for textile, the C value for all the grassy area, everything is 0.35, and then for roadway pavement, it's 0.9. So make sure that the county could have a different values too. So make sure that you are using the right parameter or coefficient. And then, so we have the C value, talking about rainfall. So, if we have done the rational method, so very common ways to use the EBD values, right? So EBD values, these three are they call the fitting equation fitting parameters, right? So you have all your data and then you have your shape, these are fitting curve or trend line. So the EBD value is the three parameter type of fitting procedure. So
I have a spreadsheet, right?
yes, so the EBD value is also location dependent. So different area you have different set. So very common one it would be the one that textiles prepared. So you can use that.
Which is what DU is using.
Yeah.
It's pulling those in.
Yeah. So that should give you the right intensity. So make sure you verify your locations first. Okay. So then we have your runoff coefficient, you have your intensity value. So that's for a rational method. And then for NRCS method, so we already know that, yeah, we have to determine our C number based on your surface typing and the soil and also your hydraulic soil group. Then you can compute your composite C number for your drainage area. So that's also, and then also, again, the peak rate factor, depending on where you are, if it's really flat, might have to adjust it. But usually the 484 the default number is good. Okay, and this one, remember we mentioned is the percent impervious cover applied
Okay.
correctly?
Not double counting it.
Not double counting it, yes. So that's very important. Then after that, then we come to, so if you're using rational methods, so everything should be done at this point because you got your C, you got your I, and you have area, you're able to determine your peak flow rates. But if you're required to do HMS, then the HMS setups right here. So you remember the three essential components. You baseline model, your climate model, and then also your control component. So those three. So you want to make sure that for your specific design storm, your intensity position with the weighting where you place your weighting, either it's a 50% center position or you're 33% on 67. So you want to make sure you follow your local criteria, and then intensity duration. Typically, this is the smallest, the TC. Also, this should be the, what is that called, the interval, simulation interval. So over here, yeah, so we have 5 to 10, but according to what we read, it's for subdivision, it's 1 minute.
Right.
So make sure that it's applied correctly. So storm area, that 1.01, this is a term that's in HMS. I think when we went through the setup, there's what's that called, the reduction factor, I think, and we didn't specify anything, right? For the area reduction.
Oh, yes, yeah.
Yeah.
We didn't specify anything.
We didn't specify anything. I think that's for a smaller area. It's not required because this is assuming that it's for point rainfall. So no area adjustment. Yeah, unless it's required by your drainage criteria. Okay. And anything, the peak flow rate check. Okay, so this is also something that we mentioned. I think it's right here.
Yeah.
So you have your area, and then remember, a good way to confirm your flow rate derivation. Make sure you're not overestimating or you're not underestimating your rainfall, your peak flow. So based on the area, based on if it's a undeveloped area or it's urbanized area, so you have a different runoff rate. You can divide it by your derived peak Q over your area, then you will see if it falls within the range.
And I think another thing that I like to do whenever I finish like the land use and I get like my weighted, I like to compare it to what I'm seeing. So if I'm seeing like a really high C value or something like that, I look at it and I'm like, well, that doesn't make sense.
Yeah.
Then I'm like, okay, because sometimes you get like boggled into like breaking it, but then you gotta step back and the overall is what you're looking for.
Yeah. So you're getting a very high C value. And then you look at the aerial image, there's a lot of green spaces. Then the problem is
Something's wrong.
yeah. But I think these numbers will probably need to verify because it's
For Austin, yeah.
it's a different region. So I think so Teresa will probably revise these before we share. Probably take out some irrelevant items. What else? We see. Okay, good.
Yeah.
Okay, and I need scrolling.
Oh, sorry. I'm like, yeah, ready.
Yeah.
Okay, so we have a different ratio here to check. And what else?
Those are like tips people.
Oh, so this is to Hydrograph best. Oh, okay. So this is talking about, let me see, component percent for this cover. Okay, yeah, that's that. So make sure your percent impervious is reasonable. Okay. And so that's pretty much, all the things that we normally would check. So starting from your watershed delineation to developing your time of concentration, land use, make sure your rainfall input is correct for your region, and then so once you get your flow rate, then you verify that if it's reasonable or not. And then if that's good, then all these flow rate can be used for your subsequent drainage design or your hydraulic analysis. So, and after that, then you check your results and the results. If the system, if the system that you design, is pretty much that you see from your neighboring system, like we mentioned yesterday. If everything looks right, then you're good. But if you, after your design or after your analysis, checking with all the field knowledge, everything, if there's any issue, you probably will go back to your hydrology and then make some proper modification to it.
Yeah, I think sometimes like stepping back and looking at it from like an overall picture. And like Ted said, when you compare it to like an adjacent system, let's say you have a crossing here and then like a few feet down you have another one. And just I guess like your peak flows for both crossings, they just don't make they're very different. Then it's kind of like a red flag. Well, something's not right. It's the same general area.
Yeah.
Mm.
Other than that, yeah, I think, yeah, that's it. And there's a lot of information and everything that we we included here. I'm pretty sure when you are actually doing your project, you'll have more questions.
For sure, yeah, that's how it goes.
Yeah. Yeah, but we try to make it really, really relevant to the actual project.
Yeah.
It's not like a standard, YouTube instruction that is
So you have
just
to like jump to conclusion.
yeah,
Easy.
yeah. So, and let us know. Just reach out.
Yeah, for sure. You can Teams me. That's fine.
I'll send you guys the pictures we took.
Okay.
Yeah. For social media or whatever it was.
Thank you.
Other than that, yeah, really appreciate it.
Yeah.
Yeah, thank you guys.
All right.
Thank you.
Are you good?
Yeah, I'm good.
Do you have any questions? I
Yeah.
know there's a lot.
Not that I can think of. I'm sure that they'll come up, but
Yeah.
Yeah. I'm hoping that yeah, if you could, I think if you guys could implement the GIS.
yeah, that's gonna be.
Yeah, I can see that. Yeah, that's the missing link here.
Yeah.
Yeah, because that will save you a lot of work,
I think I'll
time.
get started with the QGIS and then trying to dive into that, learn about it, see
Yeah.
if it can suffice, and if it doesn't.
Yeah, I'm sure it will. And there are so many, GIS, since it's a open source initiative. So even online on YouTube, there's dedicated category for QGIS learning. So you can also pick up a lot of stuff from there. Yeah. Okay. Yeah. Thank you.
Thank you.
Yeah.
Alrighty.